Hi, folks. Welcome to the Break Key. My name's Henry, and today we're getting into conditionals in the fourth ROM. So last fourth ROM adventure, we did the compile mode. We got words working. We got the ability to define new words. However, although that's great, it really doesn't help us if we're not able to do some form of branching and some form of looping. Well, today we're going to look at branching. And in order to look at branching, we need to look at conditional comparison. And in order to look at conditional comparisons, we need to look at flag values. And in order to look at flag values, we need to look into the standard. And when we look into the standard, we're going to find some interesting things about the things we need to put on the stack when dealing with all this. So let's sit back, relax, and enjoy the brain strain as we work through conditionals in fourth right here on the Break Key. So let's first look at our comparison operators. Why? Because if we have no comparison, we have no way to evaluate what's going on. And comparison introduces a new data type that we call a flag. All numbers in fourth may be interpreted as either true or false values. If you wish, 0 equals false and any non-zero value equals true, okay? A well-formed flag has a signed value of -1 or signed value of -1 for true, and as we know, that signed value of -1 is all bit set. So we have a number of them available, including a couple of words that give us a simple flag by and of itself. False gives us the binary 0, true gives us the binary -1 or binary all bit set. A flag is a single cell value as explained by the fourth standard. A true flag shall be a single cell value with all bits set. A false flag shall be a single cell value with all bits clear. So there we are. Let's begin with false and true. Been a while since I've looked at this. Let me re-verify to make sure I've got my bits and my address and my name field set up properly. Good. And that's not going to be an 81 then. False is 5 characters long, so that's going to be an 85. All right, that should be that simple. And now for true. Oops. There we are. And so those two should work. Good. All right. So, excellent. Absolutely excellent. So we know that that's working. I will start with equality. Quick aside. I need to look at signed versus unsigned. So equality, it doesn't matter whether it's signed or unsigned. Equality is equality, which is true if and only if n1 is equal to n2. When we look at our unsigns, we have unsigned less than and unsigned greater than. If I look at the standard and go to the core and see what I've got as far as comparison words, 0 less, 0 equal, let me look at the unsigned values here. It's only got unsigned less than. It does not have even an unsigned greater than, unless I go into the extensions maybe. It has an unsigned greater than. So the only comparisons we have on unsigned are less than and greater than, which makes sense because the other two comparisons are not equal and equal, which doesn't matter whether they're signed or unsigned. That's going to be an absolute value, an absolute comparison, two's complement or no. Great. So now, the beautiful thing about these comparisons is when we're doing signed comparisons, we actually have in the 6809, we have branch instructions which are signed and branch instructions which are unsigned. For instance, branch if greater than or equal to. This is a signed comparison, whereas branch if higher than, which is BHI, with the 0 flag and carry flag, if the flag is not 0, okay. The branch if higher than is unsigned. And in this case, order of operations doesn't really matter. Remember, if we're looking at the stack, if we look at how that's doing with the stack, we've got true if n1 is equal to n2. So n2 is what we're pulling into D. I think that it's not going to be, I'm thinking about whether or not this needs to be pulled out into its own code segment. I'm not entirely sure that that's going to really be a big deal because, well, no, wait a minute. How many of those am I going to use? Because the zeros, the pull UD and the compare to the zeros, I will not be doing a pull UD. But I can set up a flag. Yeah. I'm not going to be doing a pull UD, but I will be doing a comparison. With these, I will be doing a comparison with D. I will be doing a compare D. The doubles, I may not be doing a compare D. That may be something different. The unsigns, I will be doing a compare D. So it makes sense to put this into our dictionary as one of our generic subroutines, that this entire bit right here and this is for code size. If I were looking for speed and efficiency, I'd just inline it, but we're looking at code size here. This is going to be repeated, so let's move that over here to, we'll come down to the bottom. So let me look at this again, because now I'm looking at long branch subroutine. It's going to have to be an LBSR, which means that's going to take up 3 bytes in code. Compare D, let's see, pull UD. That's 2 bytes. All right, so it only has those, pull U only uses those 2 bytes. The post byte describes it just like we were talking about, or just like we saw before. So that's 2 bytes of code for the pull U, and the compare D is 2 bytes. So that's 4 bytes. Pull U, compare, 4 bytes. Now, LBSR is 3 bytes, and then we have, so that saves me 1 byte, and it puts on a performance hit. And it saves me 1 byte only for that group. All right, so it makes no sense to me, because I'll be using 2 bytes in the other locations where I'm comparing with 0. I'll be using 4 bytes where I'm comparing with with 2 items on the stack. So forget all of this. This is not going to be worth it. We'll just Control Z all that stuff right there. That is 4 bytes. You know what? I'm going about this the wrong way. Let me check and see what's going on with this, with 6809. Let me just assemble it and see what I've got. I should have done this from the outset rather than doing all this. I forgot I had this tool available. Can you tell it's been a while since I've been here? Okay, so if I do a pull UD and then I do a compare D, comma U++, how many bytes does that wind up being? That is 1, 2, 3, 4, 5 bytes. All right, lovely. So compare D U++ is 3 bytes used throughout the thing. And if I look at LBRA, that long branch is 3 bytes. All right. So literally, if I do that, I'm only saving 2 bytes, and I'm only saving 2 bytes for 4 instructions, or for 4 words. There's no sense in me doing that. I will just do this. The branching that we'll need to do will require that we have a different comparison, a different branch operator. In this case, what I want to do is BEQ, true, branch if equal to true. Otherwise, branch always. Let's see. We're branching equal to true, and then BNE. Do I want to do a BNE at that point? Yeah. Or I can put the RTS. Yep. Because BQ true has the RTS. We're already here, and I want to RTS from that. If we branch over to false, we're going to need to do an RTS anyway. So we'll do a BNE and to false and RTS. So that should work. What I believe we're going to have happen here is we'll get a true value if it's equal, a false value if it's not equal. Let's test this real quick to see how we're doing. And that gives me true. 2 and 3 equal, and that gives me false. Nice. All right. So that logic works. Let's try this now with an equal to 0. Nice. Absolutely wonderful. So next, let's look at an inequality. In this particular case, I will do a signed comparison and we'll look at less than. Return flag, which is true if and only if in1 is less than in2. Again, remember I said order of operators or order of operands didn't matter. With equality, with anything that is a inequality that is not a simple not equal to, it does matter. So let's look at less than. Oh, I completely forgot to do this. I forgot to check for stack. When we do a pull UD, D effectively becomes the left-hand side of the equation. So with D becoming the left-hand side of the equation, D was the bottom of the stack, and the way this is described, it becomes the right-hand side of the equation. So if we reverse a less than, it becomes a less than or equal to, or greater than or equal to when we reverse that. So I may want to do a trick here to make this a little bit easier. No, I don't have to do a trick to make that easier, because I have, if I'm doing a less than and it is signed, then I have a comparison. I have a branch greater than or equal to. The inverse again of the less than is a greater than or equal to. I do have somewhere over here BGE. Branch if greater than or equal to 0. So BGE is what I want to do, so I will do the pull UD. So let's see what that has to say. Assemble it. Okay. What I should see, if I take 2, 3, is 2 less than 3, and if I hit a dot, I get a -1, which is true. And if I hit 3, 2 less than dot, I get a 0, which is correct. 3, 3 less than dot, I get a -1. 3, 3, that should not have happened. Okay, so I've got a logic error, so 3 is not less than 3. And if it's branch if less than or equal to. All right, so I was wrong about the logic of the inverse operator. Lovely! It's been a while since I've done this kind of math. Yeah. We should have 2, 3 less than should show me true, which it does. 3, 2 less than should show me false, which it does. And 3, 3 less than should show me false. It still shows me true. What just went wrong here? Oh, you know what helps is if I save my work. It helps to save the source file. before attempting to assemble the source file for which changes have been made. And then we can review the changes. 3, 2, less than should be false. 2, 3, less than should be true. 3, 3, less than should be false. And now everything is nice and correct. All right. Very good. So what have we learned for this? We've learned that Henry forgot how to do inequalities properly. But now Henry has remembered how to do inequalities properly because of testing. So we've got our less than, and this will be a signed less than. It should be a signed less than. So if I take -1, and let's try that again. -1, try that again. -1, 1, less than. -1, 1, less than, dot. And that's true. 1, -1, less than, dot, 0, -1, -1, less than, dot, 0. Excellent. So, that said, greater than will not be the opposite, or will not be a not less than, because not less than will be greater than or equal to. Instead of it being a branch of greater than, and again, since that's a greater than, we invert that, that's going to be a less than, and that will be a branch of greater than or equal to. Save that. Check the assembly, looks good. Check the no debug. All right, so -1, 1, and let's look at greater than. Thumbs up false. 1, -1, greater than. Thumbs up true. 1, 1, greater than. Thumbs up false. 1, -1, greater than. I'm sorry, -1, -1, greater than. Thumbs up false. Excellent. There is a wonderful operator called not. And believe it or not, not can be written very easily as a fourth word in fourth. So if I do a define, and I say that I want that define to be 0 equal, and then I take a, oh, hang on, I did that wrong. I believe it is colon. You can tell it's been a while since I've done this. I'm pretty sure that I put the colon, and then I write the name, not. Then I'll put the variables for it. See if I can remember how to use fourth. We do a 0 equal, and then we do a semicolon. It's happy. Not's there. Lovely. We're happy. Okay. With that said, I should see this. If I put a false on there, and then I do a not, I see a -1, and I do a not, I see a -1. What that also means is now I can coerce to a well-formed flag using something that we often see in like JavaScript and other not necessarily strongly typed languages. And as we've seen here, fourth is not a strongly typed language, at least this implementation is not. So if I were to put like 27 minus 32, 32 minus, and let's see what that shows up. We come up with a -5. All right, awesome. Now, that's a non-zero number. So if I do a not, it should give me a -1. Which it absolutely does. Lovely. So if I do a 27, 32 minus, and then I do a not, that should give me a 0, which it does. So we can define not within forth itself. And this is our comparison, this is our unary comparison operator. For convenience sake, we will put that here as a word in the ROM dictionary. Assemble, make no dog. Let's see what's in the words. Not's in there. And so if I take false, dot gives me, yep, exactly. Lovely. So what about operators such as and or? Well, in JavaScript and to a certain extent in C++, and I believe also in C, those operators, and you'll see this in Bash and other places, the logical and, logical or, logical exclusive or, all of those are used not only as not only as bitwise operators, but they can also be used as flow control. That is to say, if you do something or something, then both must be executed in order to determine whether one or the other is true. But if the first one, no. That is, if you do something or something, then if the first something is true, it happens and it doesn't do the next something. But if you do something and something, then if the first something is true, it has to do the next something in order to determine whether or not it's true. But if the first something is false, it doesn't do the rest of it. We can use those as flow control. Whereas in forth, we're not going to be able to use them as flow control. It's just not designed like that. Instead, what we wind up with is a situation where we do our comparisons, like say I've got 2, 3, and I want to see if 2 is less than 3 and 3 is less than 5, all right? I've got 2, 3, 5, all right? And 2 is less than 3 and 3 is less than 5. If I want to put this together, there's a few things that I'm going to need to do. First of all, I'm going to need to take that 3 and get it on the bottom of the stack. It doesn't know what over means. It doesn't know what over means. We're going to fix that right now. Checked out. Let's assemble it. Looks good. Let's no debug it. Makes good. All right. So we'll do 2, 3, 5. That was what we're looking at. And let me do an over and then a dot, 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 dot. Yep. Okay. Good. That's exactly what I wanted to see. All right. So over is working. Now, back to that example. I wanted to see if 2 is less than 3 is less than 5. Well, in order for me to do that, I have to do 2 separate comparisons. I have to see if 2 is less than 3, and I have to see if 3 is less than 5. So I've got 3 items on the stack, as we can see, but I want to take this item right here, and I want to duplicate it so that I can compare it to 5. So we'll do an over, and the next thing I'll do, because I want to see if 3 is less than 5, is I'll do a swap, and then I'll do a less than. Okay. Now if I do a depth, I still have 3 items on the stack. Now here comes the fun part. I'm not sure if I put a rot in there or not. Did I put a rot in there? No, I didn't. More fun stack manipulation that needs to be put into the ROM. Let me make sure that I know what rot does. All right. It does a 1, 2, 3. It does a 2, 3, 1. So let's see. In which case, that brings 1 to the bottom. So what I actually want in that case is an unrot. Okay, unrot's not defined. But if I want 1 and 2, or yep, okay, so that's what I'll need to do. I can't, an unrot's not going to happen, but a rot will do fine. Hang on, let me try this. pulls you to A, B, X, Y. So it pulls in that order, A, B, X, Y. And that means that A and B should contain 1, or D should contain 1. X should contain, oh no. D will contain 3, X will contain 2, and A will contain, and yeah. Let's just run it and see what happens, shall we? Assemble. Let's try that again. Da, 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 da. Lovely. And if we do the pull. All right. That contains 3, that contains 2, that contains 1. So for the rot, what we need to have happen, I want it to push 2, 3, 1. So we push S. Say B, X, Y. So we've got the 3, 2, 1 over there, and then we've got a 1, 2, 3 over here. So what I should see is a 2, 3, 1 show up as I step through it. That did not do what I wanted it to do. All right, so let's try that again. A, B, X, Y. There we go. And if I look at what's supposed to be happening with the, yep, that's exactly cool. That's exactly what I'm looking for. All right, so there's our code. Very simple. Make no debug. All right, let's try that again. So now that we've got the stack manipulation operators here, we had 2 is 2, less than 3 is less than 5. Well, we can't do that directly because we have to do 2 different comparisons. We have to compare the 3 with the 5, and we have to compare the 2 with the 3. So we need the 3 to stick around. We over to duplicate the 3, and then we swap, and that will give me what I need. And I should be able to do a less than. Now, I have 3 items on the stack. The bottom item of the stack will be a flag, okay, which shows as being true, which is what we expect. So now I need to get these 2 items over here. So I should be able to do that with a rot, which means that I should see 3. I didn't. What the heck just happened? 2, 3, 5. Rot. Oh. Did I screw something up? That's my problem. Well, dirty. Silly question, silly things happen again. Let's get that up. Let's fix that because it's jumping to the wrong place. And now let's try. I'll bet that'll work. All right, 2, 3, 5, rot depths, dot. All right, that gives me exactly what I'm looking for, dot. All right, 2, 5, 3. Lovely. Now that I actually have what I expect to have, 2, 3, 5, rot, dot, gives me, and that should give me 5 at the top of the stack, and then. No, 5 at the bottom of the stack, 2 and 3 at the top. Yep, that's exactly correct. Good. Now we've got it worked out. Now I can actually work on the whole thing where I was looking at using the AND operator. So, control flow. Back it up. AND operator and the the logical AND operator and the logical OR operator and so many other languages can be used as flow control as well as logical comparison. However, in Forth it's different. The AND operator and the OR operator are not flow control. They are bitwise. They are always bitwise. However, they do return a numeric value which can be interpreted as a flag. So, with that said, let's start this over again. We've got 2, 3, 5. Is 2 less than 3 and is 3 less than 5? So we might write this in a normal, in another programming language is saying is 2 is less than 3 is less than 5. Okay. If we're in something like C, we would say 2 less than 3 and or no, and that's an ampersand. 3 less than 5. Okay, we would use that. But in Forth, it's going to be a little bit different. Again, like I said, no flow control there. So we put 2, 3, 5 on the stack. In order for this to work, I do need to break it up in 2 separate comparisons. All right, so in that case, I'll do an over, swap, and I'll do a less than. Okay. So that gives me 3 items on the stack, and if I do a look at the top of the stack, that gives me a -1. That gives me a -1, which is true. So we know that 3 is less than 5. If I rot, okay, the top of the stack at that point should be, it's the 3, which is what I want to see, which means that the 2 is right behind it. And if I perform the less than, and I do a do dot, that should come up true, which it does. Now, here comes the fun part. If I do an AND, this will be a bitwise AND, remember? And if I dot that, why did it come up -0? 2, 3, 5, over, swap. Dot, okay, dot, and I need a rot, less than, and that was interesting. No, it's not an overswap. It's an over. No, that's correct. Okay. We got 2. And we come up with a -256. There's something decidedly wrong here. Something has gone decidedly wrong, and how does this surprise anybody who watches these videos? And with all that frustration, I believe it's time to install some debugging tools, or at least a debugging tool for our Forth implementation. Gforth has it, and that is .s. So, for instance, if I open up Gforth here, and I type in 123.s, it gives me the depth of the stack at that point, and it gives me 1, 2, and 3. And if I do a depth, it shows me that I've got 3 items on the stack. So if I do a ++ dot, gives me a 6, and then if I do a depths, it shows me 0. So this is a non-destructive way. .s is a non-destructive way to view the contents of the stack. Tells you how many elements you have on your parameter stack and what that parameter stack is in the order in which it was pushed, and that becomes important. All right. So, because annoyance, let's make that happen. So let's look at what this little bit of magic here is doing. Let's say that I load X with, what do I have down here? Let's say I load X with 400. All right, which will be the top of the upper left-hand corner of our screen. Okay. Now I push X. All right, and at this point, what I should see once that pushes S, this should go down to 7 FFC, and I should see 400 show up over here. We'll check that each time. Next, let's try a load B with $$20, which is just a simple space, and we'll store B at the location which is pointed to by the top of the stack, and then we will pop that item from the stack by doing an increment. Because remember, as we push items onto the stack in the 6809, the value of the stack pointer, whichever one you're using, whether it be the system stack or the user stack, the value of the stack pointer decrements. We're putting on a full 16-bit word. So we have to double decrement. We have to decrement by 2, or we have to double increment to pop the stack effectively. We'll assemble the source code here. So we've got the load X0400, push SX, load B with hex 14. Let's try that again. And let's reassemble that because that was, let's reassemble that. There we go, that looks better, 20, okay. We push X onto the stack, load B, store B in S++. So if I step forward this, the first thing we're going to issue is the load X400. So we step forward on that. And X now contain, oh, that didn't work because I need an immediate value there. Assemble that. Okay. Let's step over that, and then we push. That should push 400 onto the stack, or no, that should give me a 400 on X. So X now contains 400 hexadecimal. All right, blah blah blah. Use it, whatever the heck it is. Step forward. We've now pushed that onto X. We've now pushed X onto the stack, 7 FFC, and if we look here at the memory window where the stack is located, we do in fact have 400 on the stack. Lovely. Our next instruction is going to be load B with hex 20. So there it is. B is loaded with hex 20. The next thing is to store B at the address pointed to by the top of the stack, and then increment the stack pointer. So this will, if everything works correctly, instead of storing 4B at this location, it will store B at 400. This is indirection, and it's indexed indirection. So we step. Stack is now 7 FFE, which is what we expect from double incrementing the stack pointer. And nothing changes over here because that was not destructive. It didn't change anything in memory. But now at hex 400, we have our space character, our 0x20. So that's the magic that we're doing with there, is we're storing it at the location pointed to and popping it, and this saves us a little bit of time and energy, as it were. It's good to know about indirection and pointers. And if you've never used pointers before, then I strongly encourage that you learn how pointers work. They're exceptionally powerful things. So this should be fine. Let's try and assemble and run. Actually, no debug. And let's see. Our example was 2, 3, 5, and so let's see if that works. No, it didn't. Something went terribly awry. And what that tells me is we had memory corruption, which means that I didn't return appropriately from something, or I screwed up the stack. And I have... It looked like everything was doing fine until I got to that point at B044. So let me try a breakpoint at B04. Good. Let me F5 this to get everything running. But I hate it when that happens. 2, 3, 5, S dot, no, dot S. Okay. So let's look at what's going on with our stack. Our stack is at 00E alpha and 00EA, that's 8, 9A, which contains 7FFA, and that is ECA. That is correct. Why is that there twice? I have no idea. And then that contains A359. So what should happen is I should simply head right back to where I need to be. So if I F11, LEAS, S++, and that should have my stack pointer at, okay. What just happened? Let me try this again. That didn't do what I expected it to do. Why did that not do what I expected it to do? Hang on. Because that should have changed the stack pointer location, and it didn't. All right, so... Oh, right. No, wait, no, that should have incremented S, though. Okay. I might be a little bit confused here, but here's what I think is happening. The S++ increments the stack, but it increments the stack after this value is referenced, and that value is then plugged back into the stack. All right, so, but if I change that to 2, S and run the assembly, all right, that should take care of things. And let's come back over here. Nope. Stop it, Henry. This is 4th. Except that number's wrong. So let me fix that. It helps if I make that an immediate value instead of like looking up a value. Okay. Lovely. Awesome. So now I can actually see what's going on. Let's see if we can't figure out what happened with the other thing. Like I was saying way back before, we can't just do a 2 is less than 3 is less than 5. I'm pretty sure I typed out what we were looking at with that. So what I need to do is get a copy of 3 over, a copy of 3 in front of 5. So if I do an over, That should pull 3 and put it at the bottom of the stack, which it does. 2, 3, 5, 3. That's correct. So if I do a swap, we see 2, 3, 3, 5, which gives me the ability to do the comparisons that I want to do. At this point, I want to do is 2 less than 3 less than 5. So that means is 2 is less than 3 and 3 is less than 5. So we do our less than, and let's see what we've got. We've got 2, 3, and a true. Lovely. So now I need to bring 2 and 3 down to the bottom location of the stack. Since I've only got 3 items on the stack, I should be able to do 2 rots to make it happen. There we go. We're fine. What's the less than give me? The less than gives me a -1, -1. If I AND those, I should come up with a -1 because all bits are set. Ah! That was weird. That was really weird. Okay, so something happened with .s. Let's investigate this for a minute. We'll make a deep. Let's see. Make run, and I want to set it for. Let's see. I actually do want to set it for the top of .s there, which is going to be at B1005. Okay, so we'll set that for B1005. And let's see what's happening, why this is going on. All right. So something very interesting wound up happening after the AND. I want to stop and investigate what's happening here. We are at the bottom of the stack. Stack is empty. It's saying that it's empty. Now we're running, but it says it's empty. What the heck is that? Why is the user pointer at 7FFF? It should never be on anything other than a 16-bit aligned boundary. So that means something went wrong in AND. Before I go and try and breakpoint this, let me just look at what's happening in AND. Did I seriously do that? All right. I put a U+1 in there, a comma U+1. That is an incorrect form. All right. That should be a 1, U. Is that our first one? Because maybe it went more places than that. And it did. All right. Hopefully that fixes it. So let's save it and let's try this again. So we'll do scat. I'll do make run. All right. And I will do the BP set just to make sure that everything looks right at B1005. And let's add 5 that. And let's see what's going on. 2, 3, 5. And that was going to be a over swap, less than, rot, less than. Let's see what I've got on there. And that's fine. I can F5 over that. Yep. And then I hit the AND. Whoop. Let's see. So that should give me 7FFE looks good. Let's F5 and see if... Oh, there we go. All right. So let's do this. Let's do a drop. Let's make sure everything else works. All right. So we're going to do 2, 3, 5. Let's see. 2 is less than 3, or 3 is less than 5. 2 is greater than 3, or 3 is greater than 5. So what we're going to do is a 2 is greater than 3. if I were to put this in, okay, and imagine that's a double pipe. But that's the best I can do on this screen. That's what I'm going to do. So we'll do 2, 3, 5. Again, we have to do that. We're doing 3 is less than 5, so that's going to be a over swap less than. And if I do a dot S, we're fine on that. We got the 2, 3, 1. Okay. Now, or does not matter which order they're in. So we do a rot and a greater than, and then dot S. And I come up with the 0. Good. And now, if I hit the or, let's do this. Let's do a to dupe. Okay, lovely. Let's try an or, which gives me a true. And let's try an and. That should give me a 0. Yes. Wonderful. Absolutely lovely. So, after all of that, now we have our logical comparators, and the XOR should work as well. Let's just make sure that that's going to work. -1, 0, 1, 0, XOR, dot, and it's fine. All right. So, all right. So we've got our true, and we've got our no. So we've got our logical not, which is the same as the 0 equals. We've got our comparison operators. We've got our equivalence operator. These are all signed. This is signed. This is signed. These two don't care if they're signed. We've got the true and false, colon, the bat, slash. Okay, so what about unsigned? Well, with unsigned, there's a little bit of a difference. If I look at, for instance, less than, you'll see that less than is using greater than and less than or equal. I believe I went over this before, and editor, please just kind of skip this bit if I went over this in a prior thing, because I've forgotten absolutely everything that I did before for the most part, and I'm going to review this for my own sanity's sake so that I make sure I've got it there. It is not. Is -1 in its binary representation greater than 0, which it should be, because remember, -1 is all bits set. And it is. Lovely. Yep. All right. So that should not have happened. Something's wrong there. So u less than should not have given me a -1. Oh, no, give me a 0. All right, that's fine. I don't know why I did that. No, I know exactly why I did that. Because I was silly about the stack. So if I do a -1, 0, to dupe, less than, and then do a .s there's my problem, is now I've got 0 and -1 on the stack. That's not what I want to have happen. Let me see. Oh, you know what? -1, 0. -1, 0, to dupe, less than .s. All right, so that should give me with 3 items on the stack, which is correct. And now, so I've got a flag, which is correct, but I need to do I believe I just need to do a single rot. No, I need to do another rot. Because I want to compare -1 and 0. Okay, yeah. To get the bottom of the stack over to up there, I need to do a double rot. All right, in which case now I can do the... And now it's correct. So, to make that correct, -1, 0, to do less than, rot, do less than, let's see, we're going to do a .s, depth drop in. That didn't do what I wanted to do. I probably didn't clear the stack. That's more like it. Yep. All right. So when we look at the less than, it is less than. When we look at the unsigned less than, it is not less than. That's acting correctly. Everything's fine. We're in good shape. My brain is, well, I'm actually having fun with this, despite the fact that it's going to make my brain go in weird place, but... If I take a 1 and 0 equal to, and dot that, that is, let's see, that is a false. 1, 0 not equal to. Oh, it doesn't know that? I thought I fixed that. Oh, I see what I did wrong. Missing a comma. All right. 1, 0 equal to 1, 0 equal. Dot. And that's false. 1, 0 not equal. And that's true. 1, 0 greater than. That's true. 1, 0 less than. That's false. Lovely. -1, 0 equal. That's false. -1, 0 not equal. That's true. -1, 0 greater than. Is -1 greater than 0? And it is not. It is -1 less than 0, and it is. That's working. That's working perfectly. So, that, I believe, is everything I'm going to need for now. I know that over here we also have the double comparisons, but looking what we did before, I haven't fully implemented double precision integers yet. So without that full implementation, doing those comparisons almost doesn't make sense. We're not going to be using that yet. The double precision implementations that I put in there were so I could do multiplication and division, if I recall correctly. I'll have to go back in my back catalog and look. It's been so long since I looked at this stuff. So, because frustration, because like having to do with stack manipulations and things, and I am going to call this particular episode done. We have comparisons that we can do that are both signed and unsigned and comparing to 0. They all work. And we have functioning flags, as well as, yeah, we have everything we need to generate the flags. That was a lot more frustrating than I expected it to be. But then again, when is it never more frustrating than I expected it to be? I don't know. All right, we're going to stop here because the level of frustration that I'm experiencing is enough that, and the length of video we've got so far is enough that going into flow control feels like it's going to be a kettle of worms that I don't want to deal with this episode. We'll deal with that later. We will get there. We will get there next. The next thing we will do is the if statement, the if then else, which is weird, in fourth. So stick around. Like, share, and subscribe. See you next time.